Hello there, this is lecture part 2. So what I'm going to do now is we are trying to relate Fs and Ns to Fp, Fq and the shear angle over here. Okay, so I've just copied this image. You have seen this image before. So as like before, right, we have Fp and Fq. Now what we want to find is what is our Fs and what is our Ns with relationship with Fp, Fq and the shear angle pi. Okay, so like before, I'm going to copy the length of Fp. Okay, so this is my length of Fp. So this is the direction of Fp, and then my direction for Fs. Okay, so this is my direction of Fs. Now Fs is controlled by an angle which is the shear angle pi over here. Okay, it's controlled by the shear angle, and then I have to find with relation the direction of Ns. Okay, so we know that Fs and Ns, right? So the length of Ns, so of Fs is this length. So those orange line is just to get the direction. Okay, so we know that this is our Fs, and then from here to here, coming down here, this will be our Ns. Okay, so this will be our Ns. Okay, so we can get rid of this, and we know this is 90 degrees. If you look at Fs1 and Ns1, Fs1 and Fs1 in terms of direction is the same as Fs and Ns. Okay, so both will be positive, so we can write out the relationship where Fs1 is equal to Fp positive Fp cos pi, and then you can have Ns1 is equal to positive Fp sine pi. Okay, so this is one self relationship. Then the next one is we're going to look at Fp. So we're going to copy the length of Fp again. Okay, so Fp is in this direction. Right, again it will be in the direction of Fs. So this is one direction, and then you have the other direction, just Ns. Okay, so I'm looking at the direction now. So this is our Fq, and then the first one we get, so this is our Fs2. Okay, Fs2, and you realize that the direction changes, and then Ns2, the direction is the same as Ns. Okay, so this is our Ns2. Okay, so this is our Ns2, and this angle over here is our shear angle. So from here, right, so we can find out what is our Fs2 and Ns2. Okay, so from here we know that Fs2 is equal to Fq sine the shear angle, and this one will be minus because it's in the opposite direction of Fs, so this will be minus. Okay, then Ns2 will be equal to positive Fq cos the shear angle, because the direction is the same as Ns. So from here, again, we can come up with a relationship where is equal to Fs is equal to Fs1 plus by Fs2. So Fs1 is equal to Fp cos pi minus by FQ sine pi. And likewise, you can do summation of ns. So this will be equal to ns1 plus by ns2. So you have a relationship where fp sine pi plus by fq cos pi. Okay, so we came up with this relationship, and then I would like to come up with a form where we can have tangent, tangent pi plus by beta minus alpha, and this whole thing will be equal to ns over fs. And then you ask me what angles are we taking on. Oops, sorry. So the angle that we are taking on is this angle. I'll copy the whole thing again. Okay, so the angle that we're looking down here now, okay, is this entire angle over here. Okay, so this entire angle over here is what we call pi plus by beta minus alpha. So from here, this entire term fs over ns is equal to fp sine pi plus by fq cos pi divided by fs, which is equal to fp cos pi minus by fq sine pi. So we're going to divide the numerator and denominator. So divide numerator and denominator, same thing, by cos pi. So in the end, the tangent pi plus by beta minus alpha will be equal to fp tangent pi plus by fq divide by fp minus by fq tangent pi. Okay, so the next thing that I'd like to highlight before we work on the example is we want to find how to find pi, the shear angle. Okay, we're going to find the shear angle pi. So the shear angle pi is acquired by measuring the deformed chip thickness the deformed chip thickness capital T. Okay, so how do we relate that? So I'm going to draw how are we going to relate the deformed chip thickness to the shear angle. Okay, so I'm going to draw the tool again. So this is the rake face. Okay, the clearance face. Then we have our shear angle. Okay, so the shear angle, I'm going to make it steeper down here, then it's more obvious. So we have our shear angle, then from here to here. Alright, so this is our this so-called our pi, right? And then this will be our big T, sorry, small t. Okay, so over here This will be our small t, and then parallel to the rake face is going to be a chip. So this is the chip. Okay, so this is our chip. So we want to know what is this value. We measure, sorry, we can measure this value over here. Okay, so we can measure, I'm trying to draw it 90 degrees. Yeah, this is 90, and now from here to here, right, this is your big T. Okay, so we measure, so this can be measured. Okay, this is measured, and this is determined. This is a process parameter that is set by us. Okay, so this, the small t, is a process parameter. Okay, so I'm going to call this point A. Sorry, I'm going to call this, that's not my point A. This point over here to my point A, and this point over here to my point B. Okay, and if I draw a line that's parallel, okay, so I'm going to no, sorry, so I'm going to draw a line that's parallel to my deformed chip thickness. Okay, right, and we know what we are aware of is this perpendicular line over here to the rake face. This is going to be our alpha. Okay, so we are aware that this is 90 degrees. Right, we are aware that that's 90 degrees, and we also know that this is this distance, this angle over here is alpha. Okay, so this angle over here, this angle over here, right, this angle over here, will be equal to pi minus by alpha, and the angle over here will be equal to 90 minus by pi. Okay, so we can get our pi minus alpha. So remember what I taught you guys earlier, that cutting ratio which is small r is equal to small t over by big T. And as I like to recall for you guys, that big T will always be greater than small t, and so forth. Therefore our cutting ratio will be less than 1. So this is a good thing to remember. So let's relate right, small t and big T to the shear angle pi. Okay, as I said, big T is of course experimentally. So we know, okay, that we are aware that AB is the length of the shear plane, okay, AB is the length of the shear plane. So if we use sine pi, this is equal to small t over AB. So I would like to call this my equation number 1. Then we have cos, right, pi minus alpha. So cos pi minus alpha is equal to big T over the length AB. Okay, so this is equation number 2. Okay, so from here we know that R is equal to small t over big T, right? So this will be equal to, so small t is equal to AB sine pi and big T is equal to AB cos pi minus alpha. Okay. So we can get rid of AB, so we have a relationship where R is equal to sine pi. You split the double angle, cos pi cos alpha plus by sine pi sine alpha. Okay, so you divide the top and the bottom by sine pi, get 1 over cos alpha over tangent pi plus by sine alpha. Okay, then you bring everything over, you have R, right? You can have R, so this will be cos alpha over tangent pi plus by sine alpha. The whole thing will be equal to 1. Okay. Then you introduce the R cos alpha over tangent pi plus by R sine alpha is equal to 1. So therefore R cos alpha over tangent pi is equal to 1 minus R sine alpha. So you inverse it, you have tangent pi over R cos alpha. Not inverse, you flip it over. Okay, 1 minus R sine alpha. So therefore tangent pi is equal to R cos alpha over 1 minus R sine alpha. Okay, so ultimately you get the shear angle pi is equal to inverse tangent, okay, R cos alpha over 1 minus R sine alpha. Okay, so this is how you relate the deformed chip thickness, the undeformed chip thickness to the shear angle. Okay, I'm going to stop here now. I'm going to come back with an example.